Hello and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 8, Circles, Angles, and Shapes, Lesson 8, Cavalieri to the Rescue. Starting with the Ready section. Questions or directions here say, define each figure by answering each question. And for number 1, we're going to be talking about a parallelogram. So even though it's not strictly necessary, I do think that this will be beneficial if we do a sketch. So I'll just sketch sort of a generic kind of catch-all parallelogram here. Looks something like this. Okay. So that's what a parallelogram looks like. It is a quadrilateral. So for 1A, it has 4 sides. All quadrilaterals have 4 sides. And the definition of a parallelogram is that it is a quadrilateral that has not 1, but 2 pairs of parallel sides. That's what makes a quadrilateral a parallelogram. For 1B, which sides are congruent? Well, one of the properties of parallelograms is that opposite sides are congruent. So the definition is that they're parallel, but then one of the properties that results from that is that they happen to be congruent. 1C, which sides are parallel? Well, we just said the definition tells us that opposite sides are parallel. One D, how many lines of symmetry? Well, a line of symmetry would be a line that I could draw over this figure such that if I were to fold the figure over the line, it would fold onto itself, right? So, theoretically, if I were to draw this line like that, well, that's not a line of symmetry because if I take the left and sort of fold it over onto the right, it's not going to overlap when it gets to the right. So that is not a line of symmetry. That is not a line of symmetry. And it turns out that with a parallelogram, we are not guaranteed to have any lines of symmetry. So for 1D, the answer is none. Now, if it's a special kind of parallelogram, like, say, a rectangle, then it does have lines of symmetry. But this is saying that it doesn't have to have any lines of symmetry, and the one that we drew, in fact, does not have any. E, what is the measure of the smallest angle of rotational symmetry? Well, if I take this parallelogram, if I rotate it, let's say 90 degrees, it's going to look something like this, which does not look the same as what I started with. So 90 is too small. But if I go another 90 for a total of 180, then what's going to happen is this parallelogram, if you rotate it 180 degrees, it's going to actually look more or less identical. The only thing different would be, the labeling of, vertices and things like that. But if you take away the labeling, it would actually look identical. So what that means is the measure of the smallest angle of rotational symmetry is 180 degrees. If you rotate it by anything less than that, it's not going to look the way that it did, when you started. And but if you do rotate it 180, it will look identical. Question 3 is a trapezoid, and we're going to keep going here, and we'll just do everything here. Again, not strictly necessary to sketch it, but I do think that it will be helpful when we are talking about some of these properties if we can just sort of see an example of what it is that we're talking about here. So this is sort of a generic trapezoid. A trapezoid is a quadrilateral. So again, how many sides? It has 4 sides. B says which sides are congruent. Well, in a trapezoid, um, technically none of them need to be congruent. Now, depending on the trapezoid, you can have actually up to three sides be congruent depending on the trapezoid. But if you sort of just have a generic, quote unquote random trapezoid, um, none need to be. So if I have a trapezoid that's like, say, 1, 2, 3, 4, which is certainly possible, in that situation, none of them are congruent. Part C, which sides are parallel? So this is actually the definition of a trapezoid. The definition of a trapezoid is that it is a quadrilateral that has exactly one pair of parallel sides. So a trapezoid, by definition, has exactly one pair of parallel sides. And so that would be the top and the bottom here. If it has two pairs, it's a parallelogram. How many lines of symmetry? Well, just like with the parallelogram, I cannot draw a line in this figure that is guaranteed to have the figure fold onto itself. So none. And what is the measure of the smallest angle of rotational symmetry? Well, it actually doesn't really matter. If I start rotating this thing, the only way that it's going to look identical, not 90, not 180, certainly not 270, is I actually have to go all the way around. I would have to take this figure and would have to rotate it in a complete circle and get back where I started before I get a figure that would look like my original figure. And so this one, the smallest angle for rotational symmetry is 360 degrees, which is basically another way of saying that it does not have rotational symmetry. Because anything, if you rotate it 360, you're back where you started, and so you haven't really done anything. So if a figure does not have rotational symmetry, that's more or less the same way of saying that the smallest angle is 360, because everything has rotational symmetry of 360. Question 4. Question 4 is asking us to describe a rhombus. So a rhombus looks something like this. Let's get over here. Okay. So rhombus. Oh, come on. Why is this being difficult? There we go. Okay. All right. So that's my rhombus. And a rhombus is a quadrilateral, so it has four sides. Which sides are congruent? Well, this actually gets to the definition of a rhombus. And the definition of a rhombus is that it is a quadrilateral with all sides being congruent. So by definition, all sides are congruent. If they're not congruent, it's not a rhombus. It's pretty straightforward. Also, sometimes a rhombus is called a diamond. So in a geometric context, you normally will see the word rhombus, but if it's a diamond is sort of a slightly less official, but still mathematically accurate name. Which sides are parallel? Well, this isn't the definition of a rhombus, but it's more of a property that sort of arises when you're talking about a rhombus, is that opposite sides are parallel. How many lines of symmetry? All right, so now for the first time, we've got some lines of symmetry in this figure. So one line of symmetry is just going kind of straight down, just like that. That's one. And then another line of symmetry is going across. So these lines of symmetry go through the vertices of the rhombus, and that's all that there are. So how many lines of symmetry? There are two of them. And part E, what is the measure of the smallest angle of rotational symmetry? So if you take a diamond and you rotate it only 90, well, if it's more of like a flat diamond like this one, when you rotate it, it's going to be kind of a tall diamond. So that's not what we want. We want it to look identical. But if you keep going to 180, then you are going to get another flat looking diamond. And so therefore, the measure of the smallest angle of rotational symmetry is 180 degrees. Question 6, talking about a rectangle. So you guys have known since elementary school what a rectangle looks like. Okay. So there's my rectangle. How many sides? A rectangle is a quadrilateral, so it has 4 sides. Which sides are congruent? Now, I'm noticing that none of these questions deal with the interior angle. So let me just get that out of the way right now. The definition of a rectangle is that it is a quadrilateral with congruent angles. Now, because a quadrilateral always sums to 360, and because they're congruent, that sort of implies that the angles that are congruent actually are specifically 90 degrees, because 90 times 4 is 360. So because the angles are congruent and because they sum to 360, they sort of have to be 90. But the definition of a rectangle is like I said, it is a quadrilateral with equal angles, which implies that they are 90 degrees. B says which sides are congruent. Well, you probably already know this from a rectangle, but in a rectangle, opposite sides are congruent. Also, notice that a rectangle is a special kind of parallelogram, and with a parallelogram, opposite sides are congruent. And because a rectangle is a parallelogram, well, that means that at the very least, opposite sides still need to be congruent, and that is true. So, opposite sides are congruent in a rectangle. Which sides are parallel? Again, a rectangle is a parallelogram. It is a special kind of parallelogram. And so the definition of a parallelogram is that opposite sides are parallel. And so with a rectangle, because it is still a parallelogram, this is still true. Opposite sides are parallel. Otherwise, it wouldn't be a parallelogram. And all rectangles are just specific examples of parallelograms. D, how many lines of symmetry? So in this figure, I could have one line of symmetry going vertically and another line of symmetry going horizontally. And that, I believe, is all of the lines of symmetry that a rectangle has. So it has 2. What is the measure of the smallest angle of rotational symmetry? If I take this rectangle and I go 90 degrees, it's going to be more of like a tall, skinny rectangle, which is not what I start with. If I go another 90 to 180, I will get back the same rectangle that I had before. And so here, the measure of the smallest angle is 180. I knew that was my maximum because it is a parallelogram. It's possible that it could have been less than 180 because a rectangle is a special kind of parallelogram, but it turns out that it's not special enough to change our answer for E. And so just like your generic parallelogram, a rectangle also has its smallest angle of rotational symmetry as 180 degrees. Question 7. 7 deals with a square. Just like the rectangle, you guys have been working with squares basically for as long as you've been in school, possibly before school even started for you. You've been dealing with squares. So that's what a square looks like. Hopefully that's not news to anyone. How many sides? Really hope everyone got this right. A square has 4 sides. Heard it here first. Which sides are congruent? Well, this is part of the definition of a square, in that part of the definition of a square requires that all sides be congruent. That's kind of baked into the definition of a square. So by definition, all sides are congruent. Otherwise, it's not a square. Now, the other part of the definition of a square is that not only are all of your sides congruent, which makes it a rhombus, it's also true that all of your angles are congruent, making it a rectangle. So a square is really just a special rhombus, and it's a special rectangle. So it's a rhombus because all the sides are congruent. It's a rectangle because all the angles are congruent. And in a quadrilateral, if all of your angles are congruent, it means that they have to sum to 360, and the only way that that's possible is if they are 90 degrees. And so a square has 4 right angles. Which sides are parallel? Well, again, it's a square is a rectangle, and a rectangle is a parallelogram, which means opposite sides are parallel. If opposite sides were not parallel, then it couldn't be a rectangle and it couldn't be a parallelogram. But a square is just a specific version of each of those shapes. How many lines of symmetry? So a square has a decent number of lines of symmetry. So we can go vertically and we can go horizontally. But with a square, because a square has, so many things that are congruent, it has even more. You can also go diagonally with a square as a line of symmetry. And that's off for some reason. I don't know why that just kind of shifted on me. Ugh. Hold on. We'll try this one more time and see if it's going to be annoying. Okay. All right. There's that. And then that. There we go. So a square actually has 4 lines of symmetry. It's a very symmetric figure. What is the measure of the smallest angle of rotational symmetry? Well, with a square, if you start at 0 and if you rotate it 90 degrees, you'll actually get the same square. So again, this is because a square just has so many different kinds of symmetry associated with it because everything's congruent. For a square, your smallest angle for the first time is only 90 degrees. Now, of course, if you go another 90 to get 180, you'll also get a square. So 180 will also give you rotational symmetry, but the smallest angle is not 180. The smallest angle is actually 90. Question 8. Question 8 is talking about a regular hexagon. So a regular hexagon, see how well I can draw this. All right, that's not too bad. So regular hexagon looks like this. The definition of a hexagon is that it has 6 sides. That's what makes it a hexagon. So if you didn't know that vocab, I would encourage you to try to remember that term. It's a handy term to know that a hexagon has 6 sides. Which sides are congruent? Well, notice that we're talking about a regular hexagon. And the definition of a regular, well, not just hexagon, but a regular polygon, right? So any figure with straight edges, if it is a regular polygon, it means that all of the sides are congruent and all of your angles are congruent. Like that. Notice that for the question that we just did for a square is a regular quadrilateral. and it's a regular quadrilateral because, well, it's a quadrilateral because it has 4 sides, and it's a regular quadrilateral because all of my sides are congruent and all of my angles are congruent. Regular hexagon is like the same thing, except it's with 6 sides instead of 4 sides. So which sides are congruent? Well, it's regular, so by definition, all sides are congruent. Now, obviously, you can have a hexagon that does not have congruent sides, right? If I just like randomly draw, 1, 2, 3, 4, 5, 6, that almost looks like a pentagon, but whatever. So that's a hexagon. It's just not a regular hexagon. It's also a concave hexagon. But anyway. All right. Which sides are parallel? This one, if you didn't know this fact, it turns out that with a regular polygon, if you have an even number of sides, then opposite sides are going to be parallel. So 4 is an even number. So with a square, my opposite sides were parallel. And with a hexagon, I have 6 sides. Well, 6 is an even number. And if you have a regular polygon that has an even number of sides, then opposite sides are parallel in any regular polygon that has an even number of sides. If you have an odd number of sides, then none of the sides are parallel. Okay. How many lines of symmetry? This one I think has a lot, so let's just make sure that we're not going to miss any. So with the lines of symmetry, I can go like that. I can cut through those 2 sides. I can also cut through those 2 sides, and I can cut through those 2 sides. But that's not all, because I can also cut through the vertices, like that, like that, and like that. So a regular hexagon, we're really starting to get a lot of lines of symmetry here. But how many lines do we have? We have 6. So 3 of them go through the sides, and 3 of them go through the vertices for a total of 6. And then last part is, what is the measure of the smallest angle of rotational symmetry? Now, probably the easiest way to think about this is you start at 0, and then what's the smallest angle that I could rotate this by to basically get the same figure? Well, notice that all of my angles are congruent here. And I have 6 of them. So what that means is if I take this hexagon and if I rotate it 60 degrees, what's going to happen is everything is just going to kind of fit into place. All of my sides are going to look just like the way that they do now, and all of my angles are going to look just the way that they do now. And I think you can probably see that if you do this a bunch of times, if you do 60, and then another 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 60, well, you're going to get 360 degrees. And so every 60 degrees, you end up getting the same hexagon that you started with. So therefore, the measure of the smallest angle of rotational symmetry is 60 degrees. Continuing on to the set section. Question 9 says, calculate the perimeter and area of each quadrilateral. Now, these pictures, I've got some issues with some of these pictures here. So first of all, for 9A, this 6 feet is referring to this piece right there. Okay, so BW is 6. That's what that picture is referring to. Also, we're kind of making some assumptions here. This figure certainly looks like a parallelogram, but technically we don't have enough information to assume it. But I think that this question is really trying to get us to treat this like a parallelogram. So really, we'll just acknowledge the fact that we are assuming that this figure is a parallelogram. Now, if we assume it's a parallelogram, then we can figure out our perimeter and area. So the perimeter is going to be, with any polygon, the perimeter is the sum of the side lengths on the outside of the figure. Now, we're told that this is a quadrilateral, which means we're going to add 4 things together. So if you're adding more than 4 things for perimeter, you're doing something wrong, because it's 4 sides. So when I take a look at this figure here, AD at the top is 15. Then we'll just go, I guess we'll go clockwise. DC is 10, as indicated. Now, BC is not labeled. BW is 6, but we don't know WC. However, because we are assuming that this is a parallelogram, parallelograms have congruent sides. Opposite sides are congruent, which means the entire thing is 15, which is what we want. So we're going to add another 15. And again, if this is a parallelogram, opposite sides are congruent, which means this is 10. And so we add 10. So 2 times 15 is 30, 2 times 20 is, or 2 times 10 is 20, and 30 plus 20 is 50. And perimeter is a one-dimensional unit of measurement, so it's 50 feet. For area, if we assume that this is a parallelogram, my formula for area is base times height. And what's important here is that your base and your height have to be perpendicular. They have to form a right angle. So notice that in this picture, if we treat 15 like our base, well, then the height is this dotted line because it needs to form a right angle. 10, this 10 does not form a right angle. This angle right here is not a right angle. So we can't really use the 10 for our height. We need the dotted line. Now, notice that what we have here is we have a, I'll do it in green, we have a right triangle that has one leg is 6, the other leg is 10. I don't know my height. That's not hypotenuse, that's height. And I can use the Pythagorean theorem. The Pythagorean theorem says that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. I know that my hypotenuse has to be 10, so that it has to be C. I know that one leg is 6. I'm solving for the other leg. I guess I'm calling, I guess we'll call this, I can't use B because B is going to be the base. All right, I guess we have to keep this as H then. So, actually, this was B, this is H. There we go. All right, so we end up getting 36 plus h squared is 100. Subtract 36 from both sides, and you get 64. Take the square root of both sides, so we get h equals. We know that h is a positive number, and so we do not need a plus minus here. The square root of 64 is 8, and so therefore our height is 8. For those of you that are familiar with Pythagorean triples, you may know that 3, 4, 5 is a Pythagorean triple. Well, if you multiply everything by 2, you get 6, 8, 10. So if you were able to recognize that Pythagorean triple with the 10 and the 6 and to know that your other leg had to be 8 because you can recognize the Pythagorean triple, then that's great. You do not have to use the Pythagorean theorem in this question. That's the whole kind of nice thing about the Pythagorean triples, that you don't have to go through the Pythagorean theorem and do it. But if you didn't recognize that, but you were still able to get the 8, that's just as good. It just took a little bit longer, that's all. So our area is going to be the base, which is 15, times the height, which is 8 that we just found. And 15 times 8 is 120. And we're talking about feet, and area is a two-dimensional unit of measurement, so it's feet squared. All right. For part B, again, I'm not in love with the fact that we sort of are assuming something about this shape. We're kind of assuming it's a rectangle. But we can't really solve this problem without making that assumption. So we kind of have to assume it's a rectangle. So I'll just go ahead and make that assumption. So the perimeter is the sum of my side lengths. So we'll start at the bottom this time. So we've got 15, and go to the right, we've got 10. Now, assuming that this is a rectangle, opposite sides of a rectangle are congruent, which means this is also 15. So we've got another 15, and the left has to be 10. So if I add this up, I have two 15s and two 10s. So we once again get 50 feet for my perimeter. For my area, well, the area of a rectangle is base times height, or length times width, right? It really... You take your two perpendicular lengths and multiply them. So whether you want to think of that as base times height, or length times width, or length times height, it doesn't really matter. Just try to be consistent, I guess. So here, well, this is relatively straightforward. We'll just go with base times height. I don't want to get too confusing here. So our base and our height have to be perpendicular. That's a key. Whenever you're talking about base versus height, you always need a right angle. Well, the nice thing about a rectangle is that our side lengths form a right angle. So if our base is 15, then our height is 10. And 15 times 10 is 150. We're talking about feet, and area is a two-dimensional unit of measurement, so it's 150 square feet. Part C, very similar to B. Again, we're going to assume we have a rectangle. We kind of have to make that assumption. Opposite sides of a rectangle are congruent. So this is also 15. This is also 8. So the perimeter is going to have two 15s plus two 8s. Two 15s is 30. Two 8s is 16. We add them up. We get 46 feet. Area is base times height, or length times width. My base is 15. My height is 8. And when I multiply them, I get 120 square feet. Question 10 says, compare and contrast your answers in problem 9. What do you notice about the areas and perimeters? Write a statement about your observations. All right, well, it's kind of an open-ended question. Let's just see what's happening here. So for A, for the parallelogram, our perimeter was 50 and our area was 120. For the first rectangle, again, our perimeter was 50, but this time our area was different. It was 150. And then for the second rectangle, our perimeter was different, but then we actually got the same area that we got for the first parallelogram. Right? So if we're comparing A and B have the same perimeter, but different areas. And then if we compare A with C, well, A with C, they have different perimeters, but they have the same area. All right, so let's just let's try to put that into words here. So we can make some observations here. So we identified that the perimeters of A and B are the same, but the areas are different. So they both have 50 feet, but the parallelogram had an area of 120 and the rectangle had an area of 150. Meanwhile, the areas of A and C are the same. So 120 square feet in both cases, but the perimeters are different. So the parallelogram has a perimeter of 50, whereas the rectangle has a perimeter of 46. So therefore, it is possible to have two quadrilaterals with the same area, but with different perimeters, and vice versa. So I'd say if your answer is kind of sort of like this and kind of in this ballpark, you should be fine. So yeah, same area, different perimeter, same perimeter, different area. Both are possible. Question 12. Question 12 says, the figure shows a cube with edges of length A plus B. So this is an interesting problem. I like it. It can be a little challenging perhaps if we're not careful here. Notice that this is a cube. So I know it maybe looks a little tall and maybe a little deep, but it's a cube, which means every single length is A plus B. So the length is A plus B, the width is A plus B, the height is A plus B, and you can see that. If you look here, well, this is right here. This is B plus A, which is obviously the same thing as A plus B. Right here, that's A plus B, and right here, that's A plus B. So in this cube, where every sort of face is a square, every single length, total length, is A plus B. And just by looking at it, B certainly seems longer than A. So the cube has been sliced into pieces by three planes parallel to its faces. So we've taken this cube and we've sort of cut it, we've cut it vertically. So like we've kind of cut it right along that. We've cut it horizontally. So like right along, that's not what I want. We've cut it horizontally. And then we've cut it kind of like lengthwise, like that. So anyway. All right, let's get into the actual problem. So part A, write an expression for the volume of the entire cube in terms of A and B. Well, the volume of a cube is my side length cubed. So you could take any side length, because a cube has an equal side length for any side. That's what makes it a cube. And you take that side length and you just cube it. Well, we're told that the length is A plus B. So all I need to do for part A is just say, all right, well, instead of S, we're going to say parentheses A plus B, because that is my side length, cubed. And that's it. That's my answer. That's the volume. B, into how many pieces is the cube cut? So Some of you, this might be relatively straightforward. Some of you, visualizing this might be a little challenging. Um, if we start counting the pieces, well, probably the piece that's easiest to see is the one that's like in the front. So like this piece right there, that kind of tall, kind of skinny piece, that's one piece that this cube was cut into. Then you can see there's another piece um, to the left of it, kind of a wider looking block. Then we've got this piece back here, kind of the deep piece. We can see the top of that piece right there. Then, well, we've got like what's beneath the very sort of exposed piece. We can tell that there's another piece here. We can tell that there's another piece here. So that's 1, 2, 3, 4, 5, 6, 7. There is an eighth piece, and it's hidden, right? If you were to, it's like in this area here. It's kind of hard to see. It's the eighth piece here is the only piece that we can't see, but it is there. So just because we can't see it doesn't mean it doesn't exist. And hopefully you can see how if you take a cube and sort of cut it, once, twice, 3 times, it's like you're going to have 4 pieces on the top and 4 pieces on the bottom. You're going to have 4 pieces on the left. You're going to have 4 pieces on the right. So no matter how you do this, it is cut into 8 pieces. So our answer for B is 8. How many of these pieces are also cubes? Write an expression in terms of A and B for the volume of each perfect cube that you find. So we've got 8 pieces. Of the 8 pieces, how many are themselves cubes? One of them is, one of them is right here. So if you take a look, this cube has a length of A, it has a width of A, and it has a height of A. So all 3 dimensions are the same, which means that's a cube. And so that's one of them. The other cube, well, notice that we've got A by A by A. Well, the only other sort of dimension here that we're dealing with is B for any of these pieces. And so really what we need is we need B by B by B, which is this piece in the back. Because if you think about it, you can't really see it, but there's a side coming down like that, and then like that, and then there. I don't know. I don't know if this is going to make it easier to see or not. Maybe I won't do that right now. But the other cube, we can see the top of it, and it's the top like back left corner, if you will. And you can see it's going to be B by B, and then I'll borrow this one, right? This is the height of the cube, right? So the height is also B. So to answer our question here, our answer for C is that we have 2 perfect cubes. Out of these 8 pieces, 2 of them are cubes. And if I want to express the volume, well, one of them has a volume of A cubed, and the allegedly larger one is going to have a volume of B cubed. Part D. How many pieces have a volume of A squared times B? All right. So we're looking for ones that are A by B. Well, one of them is right here, because this has a depth of A. So this bottom left front block has a height of A and a width of B, and the depth is also A. So that's an A by B. And then if we also look at the block that's in the front, so this one right here. This one's easier to see. It's this block right here in green. This is the easiest block to see in the entire picture because you can see it's A by B. So both in this case, both the red and green blocks have a volume of A squared B because my volume is A times B. And so here, I was just able to identify 3. Oh, no, wait, no, hold on. I'm getting ahead of myself here. Oh, right, we missed one. So there is another block that is A by B. Right, of course. So I knew the right answer, but I just skipped over one. So there is a third block right here. And you can see here that one of my dimensions is A, my other dimension is B, and my length is actually this value here, A. So this block kind of goes like that. So that's going to be A. Right? And then would look something like this, I guess, like that. So that block is A by B. So there's 3 blocks. There's the red, the green, and the yellow. And so it is, in fact, 3 pieces that are A by B, or A squared B. How many pieces have a volume of AB squared? Well, we can almost do this by process of elimination because we already identified that that's a cube and that's a cube. Notice that on the left here, I have A by B by B. And so this guy is going to have a volume of A times B, which is AB squared. Also notice that on the right, we have A by B by B, right? Because this is B right there. And so that is also A by B by B. Now, remember, there's that 8th piece that's hidden that we can't really see because it's in the back left on the bottom. So we can't even see any of the faces, but it is there. And that one is, I'll use, what color should I use here? I'll use lime green. We'll use this one. Purple, magenta, whatever. So the piece that we can't see, it's going to have a length of B, it's going to have a depth of B, and it's going to have a height of A because it's in the bottom. And so that's going to be A times B, which is also AB squared. So those are the 3 pieces. Those 3 pieces have a volume of AB squared. All right. So part F, write the volume of the figure as the sum of the volumes of its pieces. So I want my volume of the cube, which we said in part A is simply A plus B cubed. But instead, I want to now express this as the sum of all of my different blocks. Well, remember that we started with a cube that had a volume of A cubed. All right? So we have a single cube that's A cubed. And I'm going to write this in a specific order here that's going to make sense in a second. So we also have 3 pieces that have a volume of A squared B. That's our answer for part D. We also have 3 blocks, not cubes, but blocks, that have a volume of AB squared. We just solved for that in part E. And then we also have the other cube, which had a volume of B cubed. So the volume of the entire figure is A cubed plus 3A squared B plus 3AB squared plus B cubed. Lastly, part G. show that your answers in A and F are equivalent. So what they're saying is show that this guy, our answer for A, is the same thing as our answer for F. All right. Well, in order to do that, we're going to start with our answer for A. So we're going to start with A plus B cubed. Now, when you cube something, it means that you're multiplying it by itself and then by itself again. That's just what cubing does. So in order to multiply three binomials like this, what we kind of have to do is we have to do the distributive property twice. The first time we do it is going to be FOIL because it's a binomial times a binomial. So if I take my first two binomials here and I apply FOIL, A times A, and I need this to be in parentheses too, A times A is A squared. Now, A times B is AB, and then B times A is also AB. So I'm going to save myself a little bit of work here, and we're going to say just 2AB. So that's outer and inner combined into one term, give us 2AB. And then we have B times B, which is B squared. That's the product of my first two binomials. All right, so that is that. But then I still have the other A plus B to deal with. So let's go ahead and do this. We'll do it here. So if I distribute here, I get A cubed. Then I have A squared times B. Then I have 2AB times A. So I have 2A squared B. Then I have 2AB times B, giving me 2AB squared. Then I have B squared times A. So I have, again, AB squared. And then I have B squared times B, which is, sorry, that's a plus, not an equals. So that's plus B cubed. Ugh, that's a B. B. All right. And just to clarify here, what I'm doing is I'm doing the distributive property. So to get my A cubed, I did A squared times A. That's where my A cubed came from. Then I did A squared times B. That's where my A squared B came from. Then I did 2AB times A, which is 2A squared B. So I'm just kind of going through and I'm sort of methodically making sure that everything gets multiplied. Now all I have to do is combine like terms. A cubed, nothing to combine it with. I have A squared B plus 2A squared B. Well, that means I have 3A squared B. I had 1, and then I have 2, so now I have 3. Then I have 2AB squared plus 1AB squared, so that's 3AB squared. And then I still have the same B cubed. There's nothing I can do with that. And lo and behold, notice that this is the same as the answer that we got for F. And so we have just shown that our answers in both A and F are equivalent. We took a binomial, we multiplied it by itself twice, and that gave us a four-term expression that is the same as our answer in F. Okay, question 13. Question 13 says, if the cubes and rectangular prisms in problem 12 were rearranged, would the new figure have the same volume? Explain your reasoning. So it's saying, all right, well, you've got all these blocks here, all these colorful, now colorful blocks. What happens if we rearrange the blocks? What happens to our volume? So, okay. So, to answer this question, are they going to have the same volume? Well, Okay, sorry, we're back. In order to answer this question, we just have to understand that rearranging something has no real effect on volume. It's just like if you're talking about area, if you take a shape and move it or rotate it, as long as you don't change the size of the shape, the area doesn't change. Likewise with volume, if you have a bunch of different pieces and you move the pieces around, the volume, the total volume does not change, right? So the answer here is yes. The figure will have the same volume. The sum of the volumes of the composite pieces, so composite just means put together, will always have the same volume as long as you use all the pieces. So yes, they will have the same volume, and that is because the sum of the volumes of all the different pieces will always have the same as long as you use every single piece. If you leave out a piece or if you change the size of a piece, then that will change the volume. But other than that, your volume will be the same. Wrap things up in the Go section. Determine if each pair of solids is similar, congruent, or neither. Justify your answers. So for all the problems in this section, we've got three choices. They are either similar, they are congruent, or they are neither. As a reminder, congruent figures are identical. So they might, be turned or whatever, but basically the same exact shape, same dimensions, same volume, same surface area, same everything. If they're similar means that they are proportional, which means the ratio of the sides is the same, but one of your figures could be bigger or smaller than the other one. But as long as the same proportion is maintained, that means that they're similar. And then if that's not true, then they are neither. Okay, so congruent's identical, similar is proportional, and neither is basically anything else. So for question 15, we have two cones. And kind of right off the bat, I think it's relatively straightforward to see that these are not congruent. Right? In order for these to be congruent, they would need to be the same size, and just taking, right off the bat, the cone on the left has a radius of 1 and the cone on the right has a radius of 4. They are not congruent. Now, in order to determine whether they are similar or not, we need to check and see, all right, well, what was my scale factor that was used between these two? To keep things simple, I'm actually going to go from big to small. The order doesn't matter if you go from small to big or big to small, as long as you are consistent. I'm just going to go big to small. So if I compare my big radius to my little radius, we get 4/1, which simplifies to 4. Okay. If I compare my slant height, well, big to small is going to be 28/7, which is also 4. So far, so good. If I compare my height of the cone, not the slant height, but the height, well, my big height was 12. My little height was 4, which gives me 3. So in this case, because I did not get the same number every single time, they are not similar. So in order for these cones to be similar, I had to get the same result every single time. And if one of them is different, which in this case the height is different, it means that the correct answer here is neither. So however you want to justify this, I would just, you could show your work or you could put it into words. I showed my work here. I think it's pretty straightforward. I think that's a sufficient justification. If you wanted to put this into words, you could say something to the effect of, the height grew by a factor of 3, but the other dimensions grew by a factor of 4. Okay, so you could also sort of say that, But I think that the work that we've done here is enough justification. But you do have to have something. So let me just clarify for 15. If all you did was put neither, but you're not showing any work and you're not having any explanation, that is wrong because the directions say justify your answer. And if all you did was answer C and you left and there's nothing else, then that answer is wrong because the directions say justify your answers. So for all of these, it is not sufficient to just circle A, B, or C and move on. You either need to show some work or you need to explain it in some other way. So, 16. 16, we're talking about rectangular prisms. And again, our options are similar, congruent, or neither. So we'll start with congruent. So congruent means that these figures would be identical. And if rectangular prisms are identical, it means that they have the same length, width, and height. You know, if you sort of manipulate it, if you kind of turn it, right? So that doesn't mean that the length has to be the length and the width has to be the length and the height has to be the height. It just means that each sort of dimension has to appear in the other figure in some capacity. So for the figure on the left, we have 4 inches as our height, and on the figure on the right, 4 inches is our width. Well, that's actually fine, because again, they don't have to be in the same position. You are allowed to move the box or move the prism, and all we've done here is we've sort of moved it, so it's now 4 is no longer the height. Now it's the width. So 5 is our width on the left, and now 5 is our height on the right, and then 8 is our depth, I guess. On the left, and 8 is still our depth. So it actually turns out that these are identical prisms. They, 4 equals 4, 5 equals 5, 8 equals 8. Well, they're the same figure, so they're congruent. And if you wanted to put this into words, you just say all the dimensions are the same. And if all of the dimensions are the same, then they're the same figure. So for 16, our answer is congruent. Looking at 17. For 17, we have 2 triangular prisms. So they're prisms because they have 2 bases, although neither of these is resting on a base, but they do have 2 bases. So they have 2 bases, and they're triangular prisms because the bases are themselves triangles. So let's sort of compare what we've got going on here. Now, with a triangular prism, you can't just sort of like randomly look for, do we have the same numbers? Because with a triangular prism, you need to make sure that they're kind of sort of in the same relationship between the left and the right. So what I mean by that is if we take a look at the left, the distance between the bases is 7 on the left. It's considered the height of the prism, because if it's sitting on the base, if it's sitting on the triangle, then that would be your height. So the height of the prism is 7, because the triangles are 7 apart. And on the right, well, they're also 7 apart. So we don't need to, so that actually works out well, because that means that they're in the same spot. Also notice that the slant height of the triangle is the same as the slant height of the triangle, and that the base of the triangle is the same as the base of the triangle. So for 17, again, our answer is congruent because 7 equals 7, and 5 equals 5, and 2 equals 2. Right? And those are all dimensions, and so all the dimensions are the same. If you put that into words or just kind of show it, either is fine. 18. So we have 2 rectangular prisms here, and either by just sort of like looking at it visually or by looking at the numbers, it should hopefully be relatively obvious that this is not congruent. So remember, congruent means that they're identical. And these two boxes, they don't look identical and they don't have the same numbers. So they cannot be congruent. Now, are they similar? Well, if they're similar, it means that it means that they're proportional, which means that they have the same ratio. So again, you could go little to big or big to little. I'm just going to go big to little because I just find it to be a little bit easier. So the longer side of 15 corresponds to the 10. So we have 15 over 10. If you type this into your graphing calculator and you press math enter enter, it'll simplify it for you. If you don't have a calculator, the GCF of 15 and 10 is 5. 15 divided by 5 is 3. 10 divided by 5 is 2. So 15 over 10 simplifies to 3 over 2. My other proportion is 9 to 6. And then notice that the other one is also 9 to 6. I really only have to do it once because it's going to be 9 over 6 both times. So my other ratio is 9 to 6. Again, graphing calculator, math, enter, enter. It'll reduce it for you. If you don't have a graphing calculator, the GCF of 9 and 6 is again 3. That's not a coincidence. 9 divided by 3 is 3. 6 divided by 3 is 2. And I end up getting the same ratio. That means that they are proportional, which means our answer here is A. These two rectangular prisms are similar figures, because even though they're not the same size, the proportion or the ratio is maintained. Okay, question 19. So for 19, we have two triangular prisms, and we're told that we're told two of the sides of the triangle, and then we're told the volume. Well, all right. I think that we can eliminate congruent without too much difficulty here. These two figures, they don't look the same, and the numbers are not the same, and the volumes are not the same. So all of that indicates that these are not congruent because they are not identical. One is bigger than the other. Now, are they similar? Well, if they're similar, it means that they're proportional. And that means that the side lengths have to be in the same proportion. So we're given two side lengths. So we'll go big to small. And the 10 corresponds to the 5. 10 divided by 5 is 2. And then the other side length, 6 to 3, well, 6 divided by 3 is also 2. So that checks out. Now, you may be tempted to do the same exact thing with the volumes and say, well, the big volume is 120 and the small volume is 60, and that gets us 2, and that means it's great, and that means that the answer is similar. Well, unfortunately, that is wrong. So all that's wrong. Turns out that the answer is neither. Turns out the answer is neither, and here's why. So what we did with the 10 and the 5 and the 6 and the 3, that's fine. That's all good. With volume, if we take our large volume, which we're told is 120, and if we divide by the small volume, which is 60, we get 2, but that's not what we want. We don't want to get 2 in this case, and the reason is because we're talking about volume. Volume is a 3-dimensional unit of measurement. So the 10 and the 6 and the 5 and the 3, those are all one dimension because they're side lengths. Volume is a 3-dimensional unit of measurement, which means we don't want 2. What we want to get is we want to get 2 cubed, because the scale factor here is applied not once, not twice, but 3 times, because volume is a cubic measurement. So what we want to get is 8. And we do not get that. We get 2. So by getting 2 here, that is not the desired result if we wanted to say similar here. So we have to say neither, because even though the sides are proportional, the volume, it should be a scale factor of 8, or in the other direction it would be 1/8, but it is not that. It's only 2, and that's not good. So for 19, our correct answer is neither. Finally, question 21. I'm not a fan of, there's a little typo here. So the radii on the left are indicated with 1/, which means there really should be another slash over there, because these spheres are not the same, because 12 cubic inches is not the same thing as 125 cubic centimeters. Plus, the one on the right kind of looks bigger. So these are not congruent, right? If these were congruent spheres, they would have equal volumes, and 12 cubic inches is not the same thing as 125 cubic centimeters. One's metric, one's standard, and they don't convert easily, so one would have to be a decimal, essentially. So they're not congruent. However, we don't actually have to do any calculations on this problem at all, because we actually know that the answer is similar. And the reason that we know that they're similar is all spheres are similar or congruent. Now, if they're congruent, they're the same size. These are not the same size. However, if they're not the same size, like at a minimum, they have to be similar, because all spheres are similar. So you don't have to do any calculations with 21. You just say, all right, well, they're not congruent. My only other option is similar, because the answer for a sphere will never be neither. All spheres are either similar or congruent.